Hi everyone, this is Manuel and we are from the group 5. We are going to talk about negative staining, which is a protocol used in electron microscopy. So electron microscopy negative staining was first described by Brenner and Horn in 1965. Is a procedure used in transmission electron microscopy technique, which incorporates a thin amorphous film of heavy metal salts to highlight small biological particles on electron transparent sample support, what we call grid, to a better review of their structural details. It consists in the involvement of biological elements by an electron-dense medium, usually, as I said, heavy metal compounds, so the images are presented as a negative contrast. Thus, biological elements became clear, more transparent to electron compared to the background or the bottom of the preparation. So the electron beam can cross the biological material easier than the surrounding space. So this is a scheme of how it works. This is the side view of the preparation. This is the grid. Usually there's a carbon film on top of it, and this is the representation of the particles. Here we can see the top view in unstained specimen or without the negative staining. Here we can see the particles, we can see the background, some debris or noise or dirty. We can see it's an artifact, so we can tell exactly the difference between the particles we want to see and then the background. Everything is a little bit shady. So when we do the negative staining protocol, we're going to see something like this. The stain goes on the top of the grid and stain the background of the preparation. So we can see on the top view, the stained specimen, we can see the biological samples or the particles we want to see, the limits are more shady, and then the background more shady compared to the samples that are more clear. So the applications, we can use them in research, diagnosis, and nanotechnology tool. With variation of the technique, of course, it can be applied widely to spread biological sample types, ranging from virus to single macromolecules or macromolecular assemblies, subcellular membrane fractions such as membranes, organelles, mitochondria, or this cytoskeleton structure, lipid suspension, and so on. So there are a lot of things we can use it for. I bought here images or micrographies of this preparation. We can use, as I said, in virus. So here's a bacteriophage. The bacteriophage of the virus, it's clear than the background, as I said. Here it's a hepatovirus, which causes the hepatitis type A. It's a colony. We can see very clear. Also, we can see bacteria, the structure of bacteria. This is the Vibrio cholerae, the mycoplasm, which is also a type of bacteria, very, very small. We can see its structure. And then we can see also macromolecules. Here we can see very clear the fibers of the collagen type 1 from a rat tail. So there's a lot of applications we can use. Here at the staining protocol, that this technique will revise, improve many times throughout the years to assess and suit better to its specific biological samples. So when we are trying to apply this technique, we need to know the biological samples or what type of study we want to do, because there is a lot of type of heavy salts we can use with different concentrations, with different pHs, with the type of charge, anionic and cationic. So we need to know what type of biological sample we're going to work with to choose the better protocol. So here I brought this table. It's not exactly a very high definition, but we can see it's in Portuguese, but the virus, different virus types and different types of protocols ranging from the heavy metal salts, different concentrations of it, and different pHs. So here we can see a difference between the application. So these PTA 2% and pH 7.2, we can use rotavirus, you can use for almost everything, but we can see another type of pH here with the same preparation. We cannot use for adenovirus. We're not going to see it very clear. Another example of it, it's the same virus. Here it's the tobacco mosaical virus stained virus, negative stain reagent. So here we can see the A picture. It's very clear the difference between the edges of the virus and the background. It's very good, but when we compare to the F, for example, everything's shady. We cannot tell exactly the difference between the background and the F and the virus, for example. So we need to know what type of material, as I said, we are trying to study and learn. So about the preparation steps, usually are the same. With first we prepare the grids, which is the support must be transparent, mechanically stable during the procedure in the electron beam. So usually this is a copper grid with carbon film, as I showed before. Then we go to the pre-preparation treatment step. The hydrophilic suspension must be spread on the plastic film of the grid to allow absorption of this particle. The particles should strongly adhere to the grid surface during this process. And then we have to wash them to remove the salts and macromolecules. We don't want to stay there, interfere with the staining. And then we do the staining with the heavy metal. Staining should protect the sample structure from collapsing during the drying and providing contrast to detection of structure. It's exactly what why the technique is used for. And then we have the microscopy to find and recognizing what relevant particles we want to see. I'm going to play a quick video here with the example of the preparation so we can see clear.
If you perform this in a microbiological safety cabinet or fume hood, the grid may dry out faster. There is a separate video for preparing a higher biosafety level sample. Before you begin, gather the materials you need, which are pictured and listed. If your grid is not hydrophilized, see the previous video on sample preparation, grid glow discharge. First, mount a hydrophilized grid onto the inverted tweezers. This enables the grid to be stable during the entire procedure. Be sure the carbon side of the grid is facing out. Place 3 microliters of the sample on the grid. It is important during this process to keep the grid wet so that it does not dry out. After waiting 60 seconds, blot the excess of the sample with a wet blotting paper. Immediately after blotting, place 3 microliters of ultra-pure water on the grid and prepare a pipette with 3 microliters of stain. Then blot the excess liquid from the grid with a wet blotting paper. Immediately after blotting, place the 3 microliters of stain solution from the prepared pipette on the grid. Wait approximately 10 seconds and then blot the excess of the sample. There is an alternative method for the washing step. This alternative washing method can be used for VLPs or lentivirals to remove more debris. Place 3 drops of ultra-pure water on a parafilm. Also, place a drop of stain on the parafilm. Slide the grid on top of each water drop and blot off the excess liquid after each drop. Slide the grid on top of the stain, wait 10 seconds, and then blot off the excess liquid. Finally, store the prepared grid in a grid box until you are ready for imaging. If your grid appears to be sticky, this can be caused by an excess of sample. Next time, prepare the grid with less sample. This completes the sample preparation by negative staining.
So about the application, we brought a research article published in Journal of Applied Microbiology. So it's an original article. This group from Berlin, they tried to see the detection limit of negative staining electron microscopy for the diagnosis of bioterrorism related microorganisms. So they proved that it's this type of negative staining or this type of technique of electron microscopy, it's very reproductive and since has enough sensibility to use in this type of situation. So it's very cool. So this is our references. I hope you enjoyed. Thank you.